So this is a little rant about optimization. The deal with optimization in general in mathematics, this isn't just a calculus problem, although optimization is totally dominated by calculus. But the idea of optimization, to optimize something, means that you find the best case in a given scenario. So when you're trying to optimize, you're trying to find the conditions that give the most desirable case of something. Oops, the most case, that doesn't make sense. Of a given, in a given endeavor. For instance, what is the way to do something using where you minimize or reduce the materials or cost? That's a super big deal in like business and industry and stuff. Trying to figure out how to minimize the amount of materials you use. For instance, how to produce a box that's the right size but use the least cardboard, or how to like produce cookies from a certain recipe and at the least cost, or something like that. Cool. So that's generally when you're dealing with optimization. You're looking for conditions that give the most desirable circumstances. So you might minimize that. Or maybe you want to have, maybe you want to build a structure in your yard that will have the largest volume, so you can put all of the junk that's in your house into the structure in your yard. It has the largest volume, but maybe you want it to have the least surface area for some reason. For instance, for construction materials, you want to use the least. So for instance, maybe you want the largest volume. You want to maximize something like volume or area or something like that, profits, etc. So optimization, which is finding the kind of the best case scenario or the conditions that lead to the best case scenario. In the end, it boils down to you have some function that models your scenario, your situation, the thing you want to build, the structure of your profits or whatever. I don't understand money very well. I try to stay away from it. But like in general, whatever, you have some function that models the situation, and then you want to find the maximum or minimum values of the function, right? Like maybe your function describes the volume of the box you want to produce. And you want to find the conditions that make that volume the maximum, the largest possible, given that all the other conditions are balanced. Or like maybe your function gives the cost, and you want to minimize it. Now in these situations, I'm using economics types of analogies, just because they're easy to get our heads around, and they feel impressively practical. But this doesn't just have to do with practical things. This is with anything. Anytime you have a function and you want to find the maximum or the minimum values that would translate in a problem that might translate to the best or worst case scenarios, this is a problem in optimization. To find maximum and minimum values, AKA also known as maxima. That's the plural of maximum. The maxima are a number of things, and minima. That's the plural of minimum. So if we're looking for the maximum values of a function, we would call those the maxima. That's the plural of maximums. Similarly for minima. Cool? Usually in math, we just write max and min, actually. The max value, the min value. And that gets rid of needing to know about all of the plurals in Latin and all of that kind of stuff. So, let's see. Okay, so what does this involve? Well, let's just talk about what this would look like on a graph. The nice thing about calculus is that it allows us to use the graphical aspects of algebra to make our arguments and to think about situations. And that's really nice because geometry and shapes and drawings are really intuitive to us. So the idea is you have a function. Let's say y equals f of x. And I'm just going to draw, like, this is my favorite function, something like that. Let's assume it kind of like rises and falls at the endpoints. Cool. Yeah. Okay, so what are the maxima and minima? Oh, I know. Let's go ahead and put a little, let me do another. Let me put a few little humps in there just to make it a better example. Well, the maximum values, the maximum y values, that's what we talk about. When we're talking about maximum values, we're talking about the y values, not the x values. The heights, i.e. heights. These look like the hills or the humps, the peaks or hills, right? Like around here, that's the highest value. It gets higher up here, but around here it's the highest. Down over here, there's a little mountain peak, right? That's like the highest point there. The peaks have to do with maximum values. And you're like, got it, teach? I can spot those right off the graph. And I'm like, what if you don't have a graph? Well, we're gonna see, it's so easy, almost easier. In any event, the peaks, the highest points locally, like around any given like place on the graph, are called local maxima. They're local because like they're not like the highest. That's like the highest point, but that one's also kind of higher than the other ones around it, even though that one's bigger. And how about here? This just rises off to infinity, apparently. So there is no max. There's no maximum value. It just gets bigger and bigger over here to the right. Right? There's no maximum value because the y value is always increasing. There's no maximum because like you can even go higher than that if you keep going on out to the right. Okay, so the maxima are the peaks, the valleys. Just go ahead and put this up here. Local max is a peak, like that. Well, on the same graph, on the other hand, the low points clean this up a little. Oh my gosh, I didn't clean it up at all. I just messed it up. On the other hand, the minimum values these are the valleys or the troughs, I think is the technical term. So for instance, here, that's locally is the minimum value of the function. It goes higher on both directions. Same here. Locally, it's the minimum value. These are local minima. Remember, that's the Latin plural for minimum. These are the minimum values. Yeah, one of them is lower than the other. But locally, around where each of them happens, they're the lowest point. They're like the valleys. You can't see over the mountain to know that there's another low point there. All you know is that that's as low as it goes around there. Those are the local minima. And again, local mins, these look like the bottoms of valleys. Cool. So it's really easy to spot on the graph where the minima and the maxima are. So what does this have to do with optimization? Find the x values and the corresponding y values that give minimum or maximum values on the graph. This is the art of optimization. To find the x values that give you those y values, and also to actually give you the y values. What's the actual lowest point? What's the minimum value of this function, and where does it happen? What x value do you have to plug in to produce that? What quantity of cardboard do you need to produce the minimum cost in your box manufacturing endeavor? Okay, that's the art of optimization, is to solve for those points. So how do you do it? Well, first of all, in pre-calculus class, for those of you who have taken it, you might remember that there's one kind of function that's particularly easy to find the maximum or the minimum values of. And that's from, in pre-calculus, I'm just using an example, we use parabolas. Parabolas. A parabola is like y equals x squared. That's like the basic case of a parabola. And in general, you can find the general form of a parabola, as you might remember from pre-calculus, is going to be, so let's just say you have a general parabola, and it's like, has its, the vertex of the parabola. The vertex is the, like the bottom, the trough or the peak, depending on which way it's opening up. The vertex of the parabola represents the peak or the trough, depending on which way the parabola is facing. That has to do with the plus or minus sign in front. This has a plus sign in front. This one is opening downwards, so it would have a minus sign. You could review all of that really super easy online, or hit me up to talk about it. And you'll remember from pre-calculus that there's a very, very slick method. This parabola has a certain form, y equals minus a bx plus c squared plus d, something like this. This is the general form of a parabola. And you can use the numbers in that equation. Note that that's a quadratic polynomial if you expand it. That is, if you multiply it out using FOIL. And you can use the numbers a, b, c, and d from that to solve for the x value. You can solve for the x value and the y value to get the maximum or minimum values depending on the setup. So if you can model your problem using a quadratic polynomials, there's a totally standard, easy to pull off way to find the maximum and the minimum values just using algebra. And those of you who took pre-calculus will remember this because we make kind of a big deal about it here at UGA. I did in my class anyway. Okay, so that's one thing, that's one way to do it that you might have seen before. Well, what I'm going to show you now basically supersedes that because it works for parabolas plus all other functions that you can write down the derivatives for. That is, functions that the derivative exists, the limit of the difference quotient exists. Cool? So in general, let's look and see how would you approach the graph of a function to find those points if you don't have a slick trick like we know with quadratic polynomials, aka parabolas. If you have another function that's not a quadratic polynomial that could be redrawn as a parabola, because remember, parabolas are the shapes, the graph shapes that go with quadratic degree 2 polynomials. That's your graph shapes. That makes it really easy, and it's easy to work with these, and we know a lot about quadratic polynomials. That's a really big deal in math. So useful because we know so much about them. But for a general function, y equals f of x, how are you going to find these peaks and troughs? Well, the one main thing that you can notice about this, just looking at the graph, is that since the peak is at the top, the graph is increasing until it gets there, then it's decreasing after that. The peak represents a place that, like, if you were riding a little roller coaster car along, you'd be flat at the peak. That is, the slope at the top of the tangent line is equal to 0. Similarly, at the bottom here of this curve, come all the way down here, you're riding your roller coaster down and it comes flat before it goes back up. So here also, the slope is 0. At that point, the slope of the tangent line to the curve, that's your roller coaster you're riding, is the tangent line. And so, to find these maximum or minimum points, well, one, you have to find the slope of the function, find f prime of x, the derivative. That is the slope at all points along the curve. And then step 2, well, this is going to be a new function of x, right? You take the derivative, you get a new function. Solve the equation f prime of x equals 0 for the x values that make that true. That will find the x values. That will find this x value and this x value that go with those maximum and minimum values. Those are the conditions you need to satisfy to optimize the problem. You plug in that x value and you know that you're going to have a peak or a trough because you solved and you found the derivative was 0. Those are the places where the derivative, the slope, tangent line is 0. It's flat. So it's just a simple algebra problem. Once you've taken the derivative, you're now just solving for the roots of the equation. And then, we need to come up here for step 3. Step 3, I'm going to give you a little definition. These x values at the maximum and minimum y values are called the critical numbers, or the critical values, or the critical points. Those refer to the x values. These x values have a name. Those x values are called the critical numbers. Those are the numbers that you turn in, that you plug into the equation, y equals f of x, that will give you the critical points. Critical means it can go either way. If you're like critical, a situation is critical if it means we've got to act now, or it could go either way, right? Critical means it can go up or down. It can go left or right. At the critical points, the slope it's like a seesaw. It could go up or down. These are the critical points where the slope changes. Those are usually the points in any problem that you want to address. Stuff's just going steady. You don't need to interfere. It's at the times that things are critical that you need to know what you can do, what you can input to affect the change. And so that's what's going on here, critical numbers. Okay, now I can put step 3. And step 3 is that now you use these x values, the critical numbers, you plug these x values back into the original equation, not into the derivative. Now note, once you've solved the derivative and got those x values, if you plug them back into the derivative, it's gonna be 0. That's the definition of the roots, is that they're the things that make the derivative 0. So once you found these x values, you wanna plug them back into your original function to give you the y value, right? That y value, y equals f of x, that goes with that x value. So you're gonna plug those x values back into the original function, y equals f of x, to get the maximum and minimum y values. That easy. Like, I'm describing it as being really easy because it is this simple. You have the graph, you're looking for those places where the tangent line is flat. So to do that, you find the first derivative, solve it for its zeros, that's the places where the tangent line is flat, plug those numbers back into the original function, the curve itself, to find the height of each of these points. So easy. That's really almost everything that there is to do with optimization, except for I left out a definition. I told you about local maxima and minima. These always represent peaks and valleys. But on any given interval, whether it's a closed interval like 1 to 10, or whether it's an open interval like -infinity to infinity, on every interval, there might be like an actual like highest point, right? Like for instance, the quadratic parabola I showed you before, it has a highest point. Like this is a function that's defined on all real numbers. It just goes out to -infinity as you go that way on the x-axis, and then same thing on that direction, the x-axis. Still, out of all of the infinite values you can plug in to this function, only one of them gives you the absolute highest point, and that's over all of the values. There is a highest point. Now this function is easy to see because there's only one hump. But how can you differentiate the highest possible point? Well, number one, that is called the global max or min value. That is the highest or lowest, depending on if it's a max or a min. That's the highest or lowest point on the whole graph. Inside a specified interval. So you usually you look on a finite interval because we're not dealing with infinity in real life usually. I deal with infinity in real life every day because I get to see you all every day, and you represent infinity of brilliance and creativity and potential. But that's not a math problem. That's just the lucky position I find myself in. The global maximum and minimum is the highest or lowest on the whole graph. Cool? Like in this case, that's the global. Also, there's another couple of words that are used. Local max and mins are also called relative max and mins. Like, that's just as often used as local. It's relative. It's not the highest everywhere, but relatively, it's the highest around a certain place. And global is often called the absolute maximum or minimum value. Absolute and relative are like opposites, kind of like local and global. Okay. So if you want to find the global or absolute maximum or minimum value, that's a little bit different, but it's not much different. To find the global or absolute max and min values, if they exist, this is super easy. You do the previous steps. You find all of the local max and mins. Remember that these are y values that we're talking about, not the x values, not the critical numbers. You list off and list them out. List these numbers. So you want to be able to say, oh, well, this one has a peak there, a trough there, and so on. List the numbers out, all the local y values. Then you compute the function y equals f of x at the end points of an interval of the domain, let's say A, B, if they're closed. If the endpoints are included in the interval of that you're looking at. Okay, you compute y equals f of x at the endpoints, and then you compare these values. Compare all of the y values you've listed out in the previous steps and choose the highest or the lowest one. So the global maximum, you literally find it by hand. There's not like a math trick. You find all the local maxima and minima, the humps and the valleys. But see, maybe there's a higher point. Maybe there's a higher point at the end point of the interval. Look, here's a function I'm drawing. Here's a function I drew. And you can see that even though there's a hump there, the highest point, the global maximum, is at this end point, not at the local maximum. But on this graph, the way it looks like the local minimum is lower than this endpoint. So this actually is the global. That's the global min on this graph there. And this is the global max. Oh my gosh, that's so messy. I'm so sorry. Just on this graph, this is an example. You can see the minimum value and the maximum value that make the global min and max. So that's the deal. Those are the steps to find the global maximum and minimum. This is like, out of all possible cases, what is the most or the least that this could be? And that's everything there is to know about optimization. So do optimization, you find the first derivative, you find the roots of the first derivative, plug them back into the original function, compare those values.